For our final project for power electronics, EE4430, we did a commercialized high-side gate driver. I am Luke Volrath, and this is Nathan.
As Luke stated, we'll be doing a high-side gate driver study and to write a lab manual that taught customers how to use these gate drivers. High-side gate drivers are important because they allow you to have a load on the low side. This is very important in the application of converters. We have also learned from class that an inverter needs a high and a low side switch to function. Parts being used in our presentation include the 576-1240, which is the high side gate driver, the IRF840 LCPBE, which is the NPN MOSFETs, the TC4420 CPA, which is the low side gate driver, and then we will also be using a variety of LEDs, 100 ohm resistors, and various capacitors. We will have many circuits varied in our presentation. One of them will be a low side driver with a high side switch with a floating node. Another one will be a high side driver and a high side switch. And the last one will be a bootstrap capacitor circuit that uses 3 MOSFETs.
The schematic shows a circuit that has a low side gate driver and a high side switch. Now, as we learned in class, this should not work. However, this circuit uses a floating node power supply. If there wasn't a floating node power supply, VS would reverse bias the gate to source, and the MOSFET would turn off as soon as it turned on. However, because of the floating node, the gate voltage floats on top of the source voltage, keeping the MOSFET always in saturation. This is the low side gate driver with a high side switch in action. And the LED comes on for the win.
This is the high side gate driver with the high side switch diagram. As you can note, there is only one power supply being used and all the grounds are the same, unlike the previous circuit with the low side driver and high side switch, where that used 2 power supplies and it had separate grounds. I would also like to note that there are different capacitors within this circuit, and that is based on the different kinds of high side gate drivers. I would like to show the circuit now.
We'd like to note our homemade heatsink with a washer and a paper clip, because we are inventive engineers that don't need to spend lots of money on heat sinks. Kind of like Dr. Koh and his liquid stitch.
Now we are going to turn on the DC power supply and function generator, and as you can see, the LED lights up. This indicates that the load is getting a voltage. I would also like to note that this particular gate driver requires a 12 volt input to operate.
If you come over and look at the function generator, this is a 1 kilohertz wave with a 2.5 to 0 square wave, and the duty cycle is 50% right now, and we're going to change that and show what it does to the LED.
As you can see, I will change the duty cycle to 80%, and it brightens the LED. Now I will change the duty cycle to 20%, and it dims the LED. Now back to 50%. To the oscilloscope.
and you're viewing the wave of VDS, and this proves that the MOSFET is switching.
Would you like, just to make our last points known, high switches are needed for different applications. This circuit is much better because it only uses one power supply. It's not as expensive as the low side driver with the high side switch would be when you have to use two power supplies and separate the grounds for it to work.
This is the schematic for the bootstrap capacitor high side gate driver. V1 keeps the capacitor charged, and because the capacitor is essentially across the gate and the source of the MOSFET should always be in saturation. Next, the other two MOSFETs on the bottom are turned on by V2, the control voltage. Now, in this configuration, because both MOSFETs 2 and 3 are NPN MOSFETs, they're normally open. So without any control signal, Q1 will always be on. However, when the control signal V2 is turned on, both MOSFETs close and the source and gate voltages both become 0, turning Q1 off. So it's kind of a different configuration than some of the other configurations we've looked at, where you need a control voltage to turn the MOSFET or the switch on. In this case, you need a control voltage to turn it off. This is the bootstrap capacitor high side gate driver in action. Well, it's off right now, and we're going to turn up V1, the voltage over MOSFET number 1, until it gets to 5 volts, turning the LED on. Now we're going to come up and turn it off with the control signal by turning the control signal on. So that's the V1, the voltage over the MOSFET, and the control signal is at 0. And we just got to turn that guy up, and the LED goes off. So the load turns off, and then we're going to turn the control signal back down to 0, and the LED comes back on. Pretty cool. Okay, we're back again with the bootstrap capacitor high side gate driver to get some action shots with the square wave, because before we only saw DC. So we're going to turn on the output and the power supply. The LED comes on and the oscilloscope comes on, and we can come right up here.
First, as you can see, the MOSFET is still powered by DC voltage, but then we have the function generator hitting the signal, which used to be the V2 voltage. We have roughly the same settings as we did on the high side gate driver with the high side switch. Now we're going to come to the oscilloscope.
And this is again VDS, showing that the MOSFET is indeed switching, MOSFET 1.